Are you ready to explode your mind? Welcome to the future of creation.
Welcome to today's Explainer. We are jumping right into a really fascinating topic today, specifically Section 1.3.37, Geometrical Dimensions and Tolerances 73. Basically, we're unlocking the underlying mechanics of our modern precision-built world, the universal language of GD&T. So think about the sheer scale of the global supply chain for a second. How exactly do we prevent, utter disaster when a component machined thousands of miles away has to be made absolutely flawlessly with a part built on the total opposite side of the planet? Well, it's definitely not luck. It's a completely robust system of communication. And the answer to that puzzle is GD&T. Now, technically, it's defined as the maximum permissible overall variation of form, position, or measurements. But honestly, think of GD&T as an elegant, universal language. It completely bypasses spoken language barriers by using standardized international symbols. It tells a machinist exactly what's required to produce a perfect fit every single time.
All right, here's our roadmap for today. We're going to cover the universal manufacturing language, decode feature control frames, categorize forms and locations, establish our essential datums, and finally, look at modifiers and envelope principles. Let's dive in.
Section 1. The Universal Manufacturing Language. Just like any spoken language relies on a dictionary, so we all agree on what words mean, GD&T relies on standardized dictionaries of manufacturing. We're mainly talking about the ASME Y14.5, 2009, and ISO standards. By sticking to these strict international rulebooks, we guarantee uniformity across engineering drawings worldwide. And the absolute most important benefit here, zero assumptions. A machinist reading a drawing in Tokyo understands the exact same geometric constraints as a quality control inspector in Toronto. No guesswork involved. Section 2. Feature Control Frames Explained. Okay, so take a look at the syntax here. Notice how the feature control frame reads perfectly from left to right, literally just like a sentence in a book. We start off with a geometric characteristic symbol that tells us what kind of tolerance we're actually controlling. Then we might see a diameter symbol followed by the numeric tolerance value itself. After that, we get our material condition modifier, and finally, the whole sentence wraps up by referencing the primary, secondary, and tertiary datums. It is an incredibly logical flow once you get the hang of it. Now, at the very end of that sentence, we find the datums. Think of these as theoretically exact planes, axes, or center planes from which all our dimensional measurements are made. They're basically a coordinate system used to locate places on the part. You've got your primary datum, which is the first point of contact. That's followed by the secondary, and then finally the tertiary datum. Together, these three planes lock the physical part into a very specific spatial orientation. That way we ensure everyone is measuring from the exact same starting points. Section 3. Forms, attitudes, and locations. What's really cool is the visual logic behind the symbols themselves. If you look at the linear form tolerances, we have a single straight line for straightness and a little parallelogram for flatness. Makes sense, right? Then over on the circular form side, we've got a simple circle for routeness and a circle bounded by two parallel lines representing cylindricity. The symbols actually look like the physical geometry they're meant to control, which makes reading them a whole lot easier. And these tolerances aren't just random. They are methodically arranged into three distinct groups. First, form dictates the shape itself, stuff like straightness or roundness. Next, attitude controls the orientation between features, using characteristics like parallelism or squareness. Finally, location dictates precise coordinates relative to our datums, using symbols like crosshairs. Grouping them like this lets you instantly decode a drawing's demands. You just mentally shift from the general shape of a feature straight to its exact placement in space. Section 4. Establishing essential datums. Datums are essentially the critical punctuation marks that anchor our theoretical dimensions to physical reality. It's actually pretty interesting to see the evolution of these symbols, moving from the older style, which was just a letter between dashes, to the modern filled or open triangles we use today. But whether it's a target point, a target line, or a target area, they all serve one absolutely vital purpose: establishing the exact theoretical reference frame from which our tolerance zone is measured. Let's look at this in a practical application. Check out datum A here. Notice how the filled triangle physically points directly to the exact baseline of the component. The datum letter A is placed in its own little frame, directly connected to that surface. By doing this, the designer is loudly and clearly establishing the ultimate foundation for this part. Any other measurement referencing A absolutely has to be measured against this specific physical baseline. No exceptions. Section 5. Modifiers and envelope principles. All right, let's get into some of the advanced grammar of GD&T. One of the most powerful tools we have is the material condition modifier, and the most common one you'll see is maximum material condition, or MMC. MMC indicates that a part contains the absolute maximum amount of material permitted within its stated tolerance limits. So if you're making a pin, it's the largest acceptable diameter. If you're drilling a hole, it's the smallest acceptable diameter. Knowing this absolute maximum size is critical, because it represents the definitive worst-case scenario for guaranteeing two parts will actually assemble together. And this crucial concept of MMC ties directly into what we call the envelope principle. Notice the invisible boundaries created here. That outer red line represents the maximum material condition, literally the absolute largest this cylinder can be. Meanwhile, the inner blue line represents the least material condition, or LMC. The actual physical manufactured part, well, it can wave and fluctuate in its form between those lines, but it can never ever breach that outer red MMC envelope. It's a hard stop. So why does all of this actually matter in the real world? Well, because we've established that strict red MMC envelope for the cylinder and a corresponding envelope for the square block's hole, we absolutely guarantee assembly. Even if the cylinder has, acceptable variations in its straightness or roundness, as long as no part of its surface breaches that MMC boundary, it will always slide perfectly into its mating hole. It's basically a brilliant system of calculated clearances that prevents massive production line failures. Ultimately, this universal language of GD&T is what allows our modern, heavily automated world to function without literally falling apart. But I want to leave you with a final thought to ponder today. As CNC technology continues to advance at lightning speed and our machines become infinitely more precise, just how far can we push this? Will our geometrical dimensions and tolerances eventually reach the atomic level? Are we going to need new symbols for quantum variations? It's a fascinating frontier for sure. Thank you so much for joining me to decode this incredible language. Keep learning, keep analyzing, and I'll catch you in the next explainer.
Thank you for viewing. So far, if it gives you some information, hit the like button and subscribe for more such technical learning.